briefly about reset. I talked about the reset method, but we're going to be doing a lot of resetting in Chapter 16. And so, did we look at the KW equilibrium? We didn't finish it? All right. Let's take a look at that. H2O liquid plus H2O liquid. It's going to be a small amount of hydronium and hydroxide form. KW at 25 degrees C should be memorized. What is it? Yeah, it's 2 sig figs, so 1.0 times 10 to the negative 14. And then, did we solve the ice table for the equilibrium concentrations? Or not yet?
Well, we did solve the ice table.
And so we got the 10 to the minus 7 molar. All right. And so we know at equilibrium, this is going to be 1.0 times 10 to the minus 7 molar, and 1.0 times 10 to the minus 7 molar. Okay, that's for pure water. About what happens if we add acid to this? You know, if we add acid to this, then the acid is going to contribute hydronium. So the acid contributes hydronium. The hydronium concentration goes up. We expect a Le Chatelier shift to the left. If we add base to this, the same thing. The hydroxide would go up. Le Chatelier shift to the left. And so in the next problem, and in fact in Chapter 16, we're going to see, you know, what happens to this when we add acid. And so in this case, we're going to add, let's do a perturb step here. We're going to perturb this by adding enough HCl so that the hydronium ion concentration is 0.100 molar. So this perturb step here, we're going to put in an additional 0.100 molar. So it's going to be plus 0.100 molar plus from the HCl. The HCl is not going to contribute any hydroxide, and so this is from the HCl. And that's going to upset our equilibrium. And so now the amount of hydronium is going to be 0.100, and then I need 6 digits, or 6 decimals, and a 1, 0. And so originally we had this 6 zeros and a 1 molar. Now we have 0.1, 5 zeros and a 1 molar. The hydroxide, we carry that down, it's going to be 1.0 times 10 to the minus 7 molar. And so we were at equilibrium, and we perturbed the equilibrium. This is our new equilibrium. It's not equilibrium. It's our new initial conditions. And these new initial conditions are going to change such that we reestablish an equilibrium. But the new equilibrium is going to be different than the original equilibrium. And so let's see what happens here. Do you know which way this is going to shift? We said it's going to shift to the left. So this is going to be minus x molar, minus x molar. And so at equilibrium, I'm going to have 0.100 sub 00010 minus x molar. And this is just going to be 1.0 times 10 to the minus 7 minus x molar. And so we can figure out the new equilibrium conditions that will be established just by solving for x here. So let's go ahead and solve for x. So this is going to equal the hydronium ion concentration times the hydroxide ion concentration at equilibrium. It's just given down there, so it's 0.100 sub 00010 minus x times 1.0 times 10 to the minus 7 minus x. So just a quadratic. Let's solve for x now. And so why don't you solve this for x, and then when somebody has the x value, let me know what that is. Did everybody catch that mistake in the syllabus? Next week, Monday, it's not Washington Day holiday. Monday, there's actually lecture. And so, but it's a lecture day. I'll record the lecture day if you made plans to stay. How much more time do you need for x? A little bit? Does somebody have it? Anybody close? You know, usually you go, that's a quadratic. You know, we've been hit with harder ones like cubic, you know, fourth order, fifth order. You think quadratic should be straightforward. But I wouldn't have let it get this far, you know, because you know, immediately when I see that, I see, you know, I don't want to multiply that out. I'd rather look for some kind of trick to try to simplify the math, even though it's a quadratic, even though you should be able to solve it, no problem. It just looks time consuming. It's already been more than 5 minutes, I think. And we don't have the answer yet. Unless, is somebody close? Because I don't want to cut you off. Nobody's close yet? Like the next minute or so? All right. So, so somebody asked me, you know, for the reset, is there some simple, you know, can't you come up with some kind of clear, simple instruction on how to use the reset? The problem with is this, you know, like stoichiometry. Is there some simple, clear, you know, set of steps you can apply to stoichiometry? Yeah, in Chem 4 you probably can. You know, grams to moles, do gram to mole conversion, then do a mole to mole conversion, and then do a mole to gram. You know, I sat in on somebody's Chem 4 class, and you know, they emphasize step 1, gram to mole, step 2, mole to mole, step 3, just 3 steps. Every calculation, 3-step calculation. But is that going to really work? No, because there's so many different scenarios that pop up that we have. And so, you know, it's hard to say, okay, you follow this flow chart and you're going to be able to use it, you know, effectively. What I do is I just look, you know, if it's looking like it's going to be pain, then I immediately start looking for tricks that might or might not be effective, but, you know, I don't know if it's going to work or not, but I'm going to try it nonetheless. And so for something like this particular problem, you know, this setup looks like doable, but it's going to take me time. how much time do I want to waste? Not much. And so what I would have done is this. I would have looked for maybe resetting this. You know, I could have reset it. And in fact, if you recall the last problem I solved, you know, I skipped this. This is called the Le Chatelet's perturbation. But if we do that and we reset the perturbed initials, which way should we reset the concentration? Well, we look at the K value, and the K value tells me that this is heavily biased towards the reactants or the products. In fact, this is all reactants. And so what I'm going to do is I'm going to reset here. I'm going to reset it to see if I can make the math simpler. Now, when you reset it, you're going to consume the limiting reactant all the way to 0, whether it's forward or reverse. And when you make a 0 in initial, you have one less binomial. And so automatically that'll make the math easier. And so if we were to reset this here, what's the limiting reagent going backwards? And so I'm going to assume 100% reverse reaction, which is going to increase the amount of water, but the water doesn't change the concentration. This activity is 1, so we completely ignore it, even though I'm going to get more water. And so out of these two reagents going backwards, which one's the limiting reagent? The hydroxide. So we're going to get minus Y molar, and the most we can consume, because the 1-to-1 ratio is 1.0 times 10 to the minus 7 molar. And so basically, this is going to give us the new initial conditions. The new initial conditions would be 1.0 times 10 to the minus 7 molar is just going to be 0 molar here, where Y is minus 1. Excuse me, Y is 1.0 times 10 to the minus 7. Okay, and then we do the same thing here. We minus 1.0 times 10 to the minus 7 molar here. And then, well, that's this digit here, so we're back down to 0.100 molar. And so here are our initial conditions. And so I reset this, and now I have this. Well, now which direction is the change going to go? You know, when we reset it, we pushed all the atoms that we could to the left. We couldn't push all of them because the hydronium, there wasn't any hydroxide to react with it anymore to form the waters. All right, now when I let this reestablish equilibrium, is it going to shift right or left? It's going to shift right. I mean, it's going to go to the direction of the 0. There's a 0 here. We can only go positive. We can't go negative. So this has got to be plus X molar plus X molar. And so at equilibrium, we're going to have this. We're going to have 0.100 plus X molar and X molar here. And so now this is the K expression that we got from ice table 1. Now this is going to be from ice table 2 here, the reset table. And it's going to be 0.100 plus X times X. Now, you know, how long will this take you to solve? You know, the last K expression, you know, it was like 5 minutes and still nobody was close, at least. Or if you were close, speak up. But look at this equation. How long do you think this will take you to solve? This one should take no time at all. I mean, this is just going to be, getting it in quadratic form, it's just going to be x squared plus 0.100 x minus this term, minus 1.0 times 10 to the minus 14 is equal to 0. Now, do you have your fancy calculator? If you have your fancy calculator that solves quadratics, go ahead and tell me what x is going to be. 10? 10 times 10 to the something? Or just 10? Okay, 10 is not possible. 10 is not possible because okay, you got x is equal to 1.00, all zeros. 1.00 times 10 to the negative 13. Hey, that sounds more reasonable. Here, actually, let me turn this on. How long did that take? Like a minute? And so, do you see how much time we just saved right there? Huge. Did I know it was going to work? No. You know, I didn't know if it was going to work or not or help us, but it's worth trying, you know, just for the possibility that the math might be a lot easier. So let me turn this projector off. Okay. The projector does not want to go off now. Something's wrong with the projector. Can't turn it on. Oh, there it goes. All right, but you know what? Before solving the quadratic, I would have tried another trick because I recognize something, and that something is this. This K tells me it's all reactant. And so what I did was I reset all the atoms, or at least as many atoms as I possibly could, back to the reactant side. And so if I push all the atoms to the reactant side, how many are going to trickle back to the product side, looking at that ratio? Very few. And so what that means is that X, you know, the amount of hydronium I'm going to gain is actually going to be quite small. But hey, wait a minute, don't we know what X is already? Isn't X 10 to the minus 7? X is 10 to the minus 7 and 10 to the minus 7 because we just have water molecules colliding. No, actually X is going to be a lot smaller than 10 to the minus 7. And the way you can think about this is this. Think of this acid here as being a highly reactive agent, like you know, a tiger or some kind of predator. And you have lots of predator here. If there are no predators around, let's say this was 0 and 0, then we could build up the population of hydronium and hydroxide up to 10 to the minus 7 molar. But since there's a huge amount of predator here, what happens is, as we try to build up the hydroxide, you know, the hydroxide's trying to build up to 10 to the minus 7 molar, but it can't because there's so much hydronium in there, it attacks it immediately, and it prevents the population from rising very, very big. And so this is why the X value is so small. You know, normally in pure water, this should be 10 to the minus 7. It's only 10 to the minus 13. Why? Because there's so much hydronium there. And so that's one way of thinking about it. The hydronium attacks the population, causes the reverse reaction, and we can't build up that population as high. The other way of thinking about it is the Le Chatelier's kind of inhibition of forward reaction. The more product we have here, the less we actually have to make to satisfy the equilibrium. But immediately when I looked at this, I saw a change here, and I looked at the K and I said, hey, why not try the other trick? What was that other trick? The simplifying assumption. And so I would have saved additional time, because alternatively I could have used the simplifying assumption. Use the SA. And actually I would have done that before even bothering. I would try to do all the tricks, or except for successive approximations. It takes time. And so resetting and simplifying assumption would be all the tricks before resorting to having to do the quadratic. And so if I had done the simplifying assumption, I would have had Kw is equal to 1.0 times 10 to the minus 14, which is equal to 0.100 plus x times x. And then if we use the simplifying assumption, we're going to say that 0.100 plus x is about the same as 0.100. We don't expect to build up very much. And then x is always significant compared to 0 here. But if that's the case, why didn't I use the simplifying assumption, or why didn't I mention it on the previous problem? Take a look at the previous K expression and tell me why I didn't use the simplifying assumption, or even recommend it or suggest it for the previous setup, ICE 1. I eliminated it as a possibility because of two reasons. Yeah. If I assume that, let's go back to that one just for a moment. If I go back to the previous problem and I look, I had 0.1000010 minus, or was it minus? Yeah, minus x. 1.0 times 10 to the minus 7 minus x. This was equal to Kw. Here, if I assume that x is small compared to the initial, it would have dropped out of both terms, and then would there be any x to solve for? No. Now, you can get advanced on me. You could do this. You could be selective. So, for example, you might recognize that these are two different sized pools. For example, this, if you call this a swimming pool and we're losing a drop, then how big is this? Well, this might be like a thimble of water. If you lose a drop out of the thimble of water, it's going to be significant, because look at the initial. The initial is 10 to the minus 7. This is only 10 to the minus 1. That's 6 orders of magnitude smaller. And so I could have done a selective one where I drop the x out of the first term, but say, it might be significant in the second term, and then that simplifies the math as well. See that? But that's getting more advanced here. And it's not even worth it, because which side is this reaction biased towards? This reaction is heavily biased towards the reactant. If we're flowing the atoms towards the reactant, is it going to be a large flow or a small flow? This is the water analogy. If all the water is supposed to be on the left, but you have a lot of water on the right, if there's a lot of water on the right and we got to push a lot of water to the left, is it going to be a large flow, or it's going to be a large flow? And so in going from right to left, the change is going to be big, because it should be. We need to heavily bias the reactants. In going left to right, the change should be small. And so this is the other strategy in resetting. We reset it to the side it's biased on so that the change is always small. And so that's why we pick it that way. And so here it wouldn't have worked. The simplifying assumption would have failed. On both counts, even if we got fancy and said, oh, you know what, I can do that, but the change is going to be significant here, nonetheless. Now, over here, yeah, no problem. This should work. And so that means x is equal to 1.0 times 10 to the minus 13. How long did that take? Like 5 seconds, 10 seconds? So we have different orders. The first k expression, that's going to take, 10 minutes or something. The second one took a couple of minutes, but this one takes seconds. And so it's just using the tricks. Now, when do you know? I mean, can you determine? No, you can't really determine because, next we got to justify it. Well, the justification here is going to be clear, but, look at solving the quadratic gave us the exact same answer, so this must be perfectly acceptable. And so what is the percent change here? The percent change is going to be the change. Change is 10 to the minus 13 over the initial. 10 to the minus 13 is our change, or 1.0 times 10 to the minus 13. I'm just going to do orders of magnitude. 10 to the minus 1 is our initial times 10 squared. And so this gives us 10 to the minus 12% change. 10 to the minus 12% is way less than 5%. Many, many orders of magnitude smaller. And so in this case, it's easily justified, and this is why we get the exact same answer using the simplifying assumption as we get with the quadratic. We just saved ourselves doing the quadratic. Now, myself and the book are going to do this. We aren't even going to bother doing a perturbation here. In the chapter 16 problems, we're always going to reset it at the beginning, just like we did KW. What we did with KW is we just assumed that initially we don't have any water molecules reacting. And so this is going to be the third ice table setup. The third ice table setup is the way I do it and the way the book does it. They automatically reset it at the beginning so that the initial concentration from H2O is 0. Well, it's supposed to be 10 to the minus 7 and 10 to the minus 7. Why is it 0? Because it just makes the calculation a heck of a lot easier, and it doesn't matter if we start off at equilibrium or not, because we're going to end up at the exact same final equilibrium as long as we don't lose any atoms. And we aren't going to lose any because that's the initial from water. So we're going to assume that water hasn't reacted yet, or if it has reacted, we're going to reset it back to 0. And then we're going to have our initial from the HCl. The initial from the HCl is we're going to add 0.100 molar HCl to get 0.100 molar hydronium. And so the HCl is not going to contribute any hydroxide, and so the initial total will look like this. It's going to be 0.100 molar and 0 molar. Well, this is exactly what we did after resetting the Le Chatelier's perturbed in initial states. But we can save ourselves some addition and subtraction if we just go ahead and assume reset from the beginning. And so we always reset it from the beginning. That is, water has not reacted yet. Now, the change here, the change has got to go to the 0, so this is going to be plus x molar, plus x molar. And so at equilibrium, we have 0.100 plus x molar and x molar. And so this is the standard setup. The standard setup in this chapter is we're adding acids to water, we're adding bases to water. The water, initially, we're going to assume is 0 and 0, reset. And then we're going to add the acid, however much acid we have, 0.100, 0.200, 0.500, 6 molar, whatever. We're going to plug it in here to get our initial and then figure out what's going to happen after that. Are there any questions on this? I skipped some steps, but we'll look at those steps next time, next week. But all the calculations are going to look like this, basically. So that makes it easier because then the reset is pretty clear. All right, let's move on to lab. Which ion are we going to analyze next? Lab. So we finished off with iron, is that correct? And so the next one would be aluminum. Let's look at the aluminum analysis. For aluminum, we start at the very beginning. The very beginning would be step one, where we took our unknown aqueous and added HCl to this. If aluminum ion is present, what happens when we add HCl to it? Nothing. Right? Nothing happens because this should be a selective reaction. We want the silver ions to react with the chloride, but the aluminum 3+ we don't want. Otherwise, we're going to get a mix of precipitates, for example, silver and aluminum. And so this is important for the separation of silver ions from the rest of the cations. The rest of the cations better not precipitate, at least the ones on our selected list. Okay, after we add the HCl, then what do we do? We take the solution from 1 and add this. NH3, NH4+, what did I call that? Buffer. Yeah, that buffer. Buffer helps us control how much hydroxide we have in solution. Do that. And we should get a, almost a colorless or very, very faint white precipitate. It's not a very dense precipitate. It doesn't sink to the bottom like silver chloride. It just kind of floats. It's low density. Forms like wispy clouds of precipitate. The equation for this will be aluminum 3+ plus 3NH3 plus 3 waters. This is going to produce aluminum hydroxide. The aluminum hydroxide precipitates and drives this reaction, plus 3 ammoniums. What kind of reaction is this? Metathesis. Why are we adding ammonium? Ammonium is a product. Why are we adding ammonium? Will adding ammonium help form more precipitate? By adding ammonium, can I get more precipitate? No, actually I'm going to get less precipitate. But wasn't it important that we do complete precipitation? Except here. Why?
Looking for the presence, not complete yield.
Well, yeah, for all these we don't concern ourselves with yield, but we still try to get complete precipitation because we don't want anything contaminating or decantate. That is, if we don't get rid of all of a particular ion, then it can seep through and cause side reactions or unwanted reactions to occur in subsequent steps. But the addition of ammonium wasn't for aluminum. The purpose of the ammonium was for other ions, like magnesium. What don't we want to happen with magnesium? We don't want it to precipitate. We don't want the 2+. We only want the 3+ cations to precipitate. And so the ammonium's there to help prevent the 2+ cations, which are a bit more soluble than the 3+. The 3+ are highly insoluble, and so we barely need any hydroxide, but the 2+ require a little bit more hydroxide to precipitate. And so by having the ammonium in there, we can prevent precipitation of those 2+, potentially 1+ cations. All right, what's the next step? One thing that helps a lot is to have the flow chart always handy. If you have the flow chart handy, then you can kind of quickly see where you are. You know, it's like if you're in some unknown neighborhood and you're driving around, if you have the map there, then you can kind of get a quick overview of where you are. But if you're on some street and you have no idea where you are, it's pretty easy to get lost. Everything starts to look the same. And the same thing with this procedure. You know, if you're in this sentence in the middle of some big paragraph, it's kind of hard to see where you're at. People have always come up to me, you know, what should I do next? I'm at step 5C. I said, okay, what do you have? I don't know. Those already happened to me 3 times today. They're at step 5C. They don't know what they should do next. I ask them what they have. They have no idea, and so then I tell them, you know, you should take a look at the flow chart and try to correlate where you are there with the flow chart. And so take a look at the flow chart and see what we add next. Try to find aluminum hydroxide and tell me what's added next. Peroxide. Is peroxide added or hydroxide added first? Is hydroxide? And so you can pen that in if it's not in the flow chart. But we're going to add hydroxide. So we're going to take our precipitate from 2 and then add sodium hydroxide. And then we're going to see the precipitate dissolves. And what we have here is we have the aluminum hydroxide, solid, and what's going to happen is another hydroxide is going to attack that. When it attacks that, it's going to form this. Can you name that? Species on the right? Yeah, tetrahydroxoaluminate forms. The tetrahydroxochromate does not form, and tetrahydroxo, what's the other one? It's the other 3+. Ferrate. Tetrahydroxoferrate doesn't form. And so just aluminum. Why? Well, these types of reactions are complicated to predict. What kind of reaction is this? What kind of acid-base reaction? Lewis acid. Lewis acid-base reactions aren't easy like Bronsted. Bronsted are easy to predict. Lewis are more complicated. And so, how do you know what forms? We look it up in a table. We saw somebody already did this. This is what formed. So we can use that information for our prediction. Okay, now we are going to add what? The hydrogen peroxide? Does that come next? Yeah. And so we add it to this. Or we add it to the solid residue, or do we decant, or do we do a separation, or do we just... We add it to the precipitates? Okay. All right, so the next step, well, the sodium hydroxide will dissolve our aluminum, and so it's going to go into solution, and so we're going to take solution 3 and then add hydrogen peroxide to it. Hydrogen peroxide is typically thought of as an oxidizer or reducer.
reducer. It's actually, it can go both ways. It can be an oxidizer or a reducer. Which way does it prefer? In the sense that which way is it stronger? Is it stronger as an oxidizer or is it stronger as a reducer? Oxidizer. It's stronger as an oxidizer. It's like, what's its ranking in oxidizer strength on your chart? Yeah, it's up there. It's near the top, right? Near the top. So typically, hydrogen peroxide is thought of as an oxidizer. What's going to oxidize? Aluminum, right? Hydrogen peroxide will have a hard time oxidizing hydroxide. And so we end up with no reaction. And so we have our tetrahydroxoaluminate plus hydrogen peroxide yields NR. I don't know if anybody's claimed to make aluminum plus 4. I'm sure somebody's made it, you know, but as a stable compound that can be isolated would be tough. Maybe in the gas phase as an ion, might be possible. All right, so we don't want reaction here because the purpose of the hydrogen peroxide is not to react with aluminum. The purpose of the hydrogen peroxide is to react with what? We wanted the hydrogen peroxide to react with the chromium-3 to convert it into chromium-6, which is chromate, right? And so that's the purpose, but we have to show this because if hydrogen peroxide reacted with both chromium and aluminum, then we need to know what's happening there. And so this is why we write these. A lot of people say, why do I have to write the no reactions? Because no reactions are critical steps in the separation of the ions. Next, what do we add after the hydrogen peroxide? Hydrochloric acid. All right, so what we're going to do is we're going to take solution 4 and then add HCl. And what forms upon addition? So just look at the flow chart and tell me what forms. You just follow from one box to the next box. Do you see what box is below the tetrahydroxoaluminate? At the arrow should be some HCl. No. Aluminum 3+. And so here it appears like no apparent reaction, but there is a reaction. The reaction is we're going to destroy the complex. You know, the hydroxyl ligands are basic. We add some acid here. Let's add 4 H pluses. We're going to get Al3 plus, the plus 4 water. And so we have the hydroxyl complex, but we're going to destroy it using some acid. We'll look at these types of reactions much more in depth in chapter 18. Okay, after adding the HCl, then what? Okay, are we adding the buffer? So we're going to take solution 5, and then we're going to add ammonium, or just ammonia? Why no ammonium? We want the weakest strength or the middle strength? Is this middle strength? This is stronger. The weakest was the buffer. This is middle strength, and the strongest was not NH4, just NaOH or sodium hydroxide. So we're using the mid strength, but didn't I say we need to use the buffer because we don't want the group? We don't want the other ions to precipitate, and so we run the risk. Like for example, if I had magnesium ion and I added aqueous ammonia like this, then the aluminum and the magnesium would precipitate together, and they would be both white precipitates. And so the question is why don't I use the buffer here when I used it before? What do you think?
Because you made it into a compound and then broke it down. You already used the sodium hydroxide.
Yeah, so that's kind of it. I mean, here you're right. We're using full strength here. Why is it okay to use full strength here? Because here I'm using the weakest, and then all of a sudden I jump to full strength. Does that make sense? Because we didn't want to use full strength because full strength would be detrimental in the sense that it can precipitate other cations that we don't want to precipitate, like Mg2+, etc.
But the full strength doesn't precipitate anything, it dissolves precipitate.
Yeah, but why doesn't it precipitate? Then why didn't we use it here? Why didn't we use the full strength here? Because then I could have just saved a step, just not even bother precipitating and then just went straight. Or, I got 3 hydroxide precipitation steps so far. I'm precipitating oh no, this is not it. Alright, number 1, I don't want to use full strength here. If I use full strength, I might not get the precipitate. If I use full strength and I just put a slight excess, what's going to happen to my precipitate? So what's going to happen is this. If I use full strength hydroxide, I'm going to see my white precipitate grow, and then all of a sudden it's going to start shrinking and disappear. And so you're thinking you're doing good because you're adding more and more hydroxide, but that additional hydroxide is just dissolving, eating away your precipitate until you're left with no more precipitate. So we don't want to use full strength here. But we don't want to use full strength. Why not use medium strength? Ammonia. Why do we have to buffer it with ammonium? And the reason is because there are other things going on here. The other things going on are this. When we precipitate this out, we're precipitating aluminum, chromium, and iron. And then we're separating out all the other ions that might potentially interfere. Those are called interfering ions. Those interfering ions would have precipitated out here, like magnesium loves hydroxide, and we don't have to worry about complexes here. So if I had magnesium present at this step, then I would have gotten a mix of hydroxide precipitates. But I'm not, because I've already separated it out in this step, which I'm not showing. And once I get over here, there's nothing else left. The only thing I'm going to precipitate is aluminum 3+ because I've removed all the other cations. And so when I add this, I'm going to get a white PPT. And the reaction just looks the same. It's going to be Al3+ plus 3 ammonias plus 3 waters gives us aluminum hydroxide, solid plus 3 ammoniums. All right, what's next?
Chromium.
Oh, not we're still on the aluminum branch. So what's next? The next step for aluminum down the flow chart. HCl. And so what we're going to do is we're going to take the in step 7 we'll take the precipitate from 6 and then add HCl to this. The precipitate from 6 plus HCl, we'll just see the precipitate dissolves. And that is aluminum hydroxide plus 3 H pluses will form Al3 plus 3 waters. Just a metathesis or an acid-base reaction here. So aluminum hydroxide solid. Okay, what's in the next step here? Okay, the aluminon reagent. And so what we're going to do is we're going to take solution 7 and add what to it? Aluminon and NH3. So we're going to add NH3 and then aluminon. Aluminon I'm going to write over the arrow. Because when I take aluminum ion, Al3 plus, and react it with ammonia, what's going to happen? Aqueous ammonia. Yeah, I'm going to actually precipitate. Aqueous ammonia precipitates out hydroxide. I'll precipitate out aluminum hydroxide, solid, plus 3 ammoniums. Okay. But there's a difference, and that is, what exactly is aluminon? Aluminon is an organic dye, and what happens is this dye gets incorporated in the crystal lattice of aluminum hydroxide as an impurity. And so all we need is a little bit of aluminon to get trapped in that lattice. When it gets trapped in the lattice, it discolors the precipitate. In fact, aluminum hydroxide should be white, but in the presence of aluminon, that precipitate is actually red. And so what we do is we centrifuge it down. And so these wispy clouds of precipitate will pack down. When they pack down, what it resembles is this. The precipitate is going to look like a red lake. It's just a gelatinous layer, and when you look at the surface, it looks like a liquid surface. It's not a lake, it's not a liquid, it's actually a solid. And then we're going to have the supernatant above it. The supernatant above it, or I shouldn't call it supernatant, what should I call it? Decantate? Is that what they call it? The decantate above it looks like the sky. And so what it looks like is it looks like you made a miniature lake inside your test tube. There's a red lake here, and then the clear liquid above it, the clear colorless liquid, looks like the sky or the air above the lake. But you have to be careful because we aren't looking for a red solution or red liquid, we're looking for red solid. And so this definitely should be a precipitate. And so what we need to do is we need to centrifuge this, otherwise it doesn't work very well in order to see the red lake. And so the red lake is this dyed aluminum hydroxide precipitate, which turns red. Other ions don't necessarily form a red lake. They precipitate out the hydroxides. All right, I'm going to stop here and let you work. Most of the lab. Are there any other questions on homework, chapter 15, or the lab. A lot of people in the morning class, not a lot, but about 5 people in the morning class finished the known. And so some of them started the unknown today. And they're fast. I mean, that's fast to finish the known in one day, pretty much. If you have practice, it's easy to finish it in one day, but it's a pretty fast pace, and I'm not sure the quality of the work. But before you start your unknown, you have to be careful. You know, let me give you a bit of advice. I didn't give this to morning class because I didn't realize people were already finishing, but I'll tell them next time. Do you remember how I said that the people who followed the instructions precisely aren't doing a very good job? And so what tends to happen is something like this. Let's say they didn't have any aluminum present, and the instructions say add 10 drops of HCl. They don't have any aluminum present, they add 10 drops of HCl. And then over here it says add 20 drops of ammonia. They add the 20 drops of ammonia. And pretty soon the solution volumes are changing significantly. The HCl is making the solution acidic, the ammonia and the hydroxide is making it basic. And all that time, you know, it's making it way too acidic and way too basic because most of the H plus should react here, right? And be neutralized. But when there's nothing to neutralize it and you continue adding a whole bunch of H plus to it, we say the pH goes way down, and other stuff can happen, you know. Or here the pH goes way up. We have these wild fluctuations in pH. That's because all these reactants aren't reacting. In this case, though, they would be reacting because here we'd be neutralizing the HCl with the NH3. And so that means we're continually modifying, but you think, well, how do you modify it? Well, the way you modify is very simple. You just look at what you're trying to do and then just do just enough to do what you set out to do. That is, just add the right amount being just enough to do what you set out to do. Well, what are you setting out to do? You could look at it in the flow chart to figure out, you know, what you're trying to do at a particular step. And so a lot of people come up to me, including this morning, I added 4 drops here. You know, nothing happened. Well, what do you expect to happen? I don't know. The instructions said to add 4 drops. Well, you know, that's not good because you should always be aware of what you expect to happen, because that way you can tailor the amount of reagent that you use to accomplish it. Okay? All right, that's all, and that's going to be critical when it comes to the unknown. So I know a lot of people, even though they finish their known, I told them maybe you want to repeat the known again, you know, just to get more comfortable with the procedure. I don't know where you guys are at, though, but